Okay, good afternoon. This is the title of my talk, and as the previous two speakers, I have also some controversial things to tell you, and probably also can be a little bit provocative to try to solve them. So you may have listened or read this statement: the three-finger toxins have a low molecular mass. This is true, and are therefore poorly immunogenic, thus presenting a challenge to the generation of high antibody titers in animals that are immunized with venoms that contain these toxins. Well, if you know from any experimental evidence for this, raise your hand. It has been repeated and repeated in the literature, but we will go later to Andreas that says he has an experimental. We have done an experimental testing of this hypothesis just by comparing the horse immune system response to toxins versus crude venoms. So if they are poorly immunogenic, we should see the result in this experiment. So for this, we have first set up a platform for large-scale purification of medically relevant toxins, which are the ones that we will be using for immunizing horses versus a whole venom from which these toxins were produced. And when I mean large scale, is scale is purifying the scale of grams or dozens of grams for doing all this research. And also here is an example of this particular toxin that is purified at 1.7 grams in a couple of days. So this can be done easily if you have the starting material. So with this toxin, we have generated toxin-specific affinity columns and isolated antitoxin class antibodies against the immobilized toxins. What we do is we set these three affinity columns where we have immobilized a single toxin. It's called the ITX, which can be the same as the immunizing toxins or another, I will show in another example. So the binding capacity of the toxin is in the range of 12 to 16 milligrams of toxin per milliliter of matrix. And what we do is to load a certain amount of hyperimmune serum, either against the venom or against the toxin, wash the column, recover what is bound to the column, the non-binding material load on a second column, do the same, take what is in the column and do to a third time in a third column. Usually with two columns, you recover all what is recoverable from the starting material. So from at saturation, the L weight of column 1 gives you a view of the milligrams of specific anti-immunizing toxin per gram of immobilized toxin in the matrix. And the sum, the combined L weights, 1, 2, and 3, is the percentage of the specific antibodies, anti-immobilized toxin, in this case, corresponds to the immunizing toxin that are in your starting material. In another experiment, we immunize with one toxin and immobilize another one. So in this case, we want to see whether there is paraspecificity and quantify this paraspecific reactivity. We do the same, wash the column, recover the paraspecific antibodies, and in this case, of course, the paraspecificity is not as high as the specific reaction, and you get less. But and you have here the same. In the L weight of column 1, you can measure the paraspecific activity of the antibodies that you are recovering in terms of anti-immunizing toxin per gram of of immobilized toxins, which are paraspecific between themselves, are not exactly the same. So in this table are the results, and as you see here, from the recovery of per gram of immobilized toxin, you have a much better result than when you use the whole anti-NAYA, in this case, anti-serum, that was the primary source, isolating also these antibodies. So here, and these are results that we had from other results in the laboratory against commercial premium serum, Samir, and Fabafric, the old Fabafric. What about the percentage of antibodies against three-finger toxins, against neurotoxins, against cytotoxins, and against PLA2. And you see that these results in terms of percentages are lower than the ones that we obtained using this antitoxin anti-serum. So it seems that at least with antitoxin and with toxins, you get much better immunization than if you use the venom, the complete venom. So here you see the differences between 1.5 to almost four times more antibodies when you use purified toxins than when you use the primary venoms that are the most conventional way of immunizing horses to produce polyvalent antivenoms. So these are the data for in milligrams of antitoxin antibodies per gram of polyspecific antivenom, and these are the same but per gram of antitoxin antivenom. So it's much better with the isolated toxin. So from these results, one can confidently say that this statement is fake. It's not the case. It's not the toxins are low immunogenic. It's that the way you present to the horse is not the most adequate to raise antibodies in this animal. So we also did some analysis and venomic analysis, proteomic analysis on the antivenoms, antibodies. And here we have anti-SOR neurotoxins, anti-lung neurotoxins, anti-cytotoxins 1, 2, and 3, and PLA2, non-reduced and reduced. And what we did is to try to calculate the number of different antibodies that you can these toxins have raised in the horse. And what we apply is a kind of Tetris-like experiment where we cut the bands of the full antibody in the heavy and the light chains of the FAB2 fragment, and do LCMS and align all the tryptic peptides that we obtain on a template, any template where you can align them, and you complete the first line with all the fragments that you can put that have homology to the template. When you find one peptide that contains different sequence but aligns in a position that is already occupied, you start the second line and so on. It's a Tetris-like approach. So the number of lines are a proxy of the number of different sequences, which mean of the number of different antibodies that you have in your sample. If you look here, this is an example. I put in different colors fragments that have different sequences, so different antibodies. And for these SOR neurotoxin antibodies, we found consistently between 2 and 5 different antibodies. So these low immunogenic toxins raise not only better titers in terms of antibody, but also a large large number of epitopes are involved, in this case between 2 and 5. And the same happens for the long neurotoxin and the cytotoxins. This is one cytotoxin. This is also PLA2. This is another cytotoxin. By the way, this was a cytotoxin, a paraspecific one, not the specific, but the ones that we isolate antitoxin in a paraspecific manner. So we also perform in vivo studies on the potency of these anti-single toxin antibodies for the same toxin. And here you see that for the short neurotoxin, we have a type of 28 milligrams of toxin neutralized per gram of antitoxin, of the homologous antitoxin. And if you take into consideration this means that this potency is equal to a potency for whole venom at about 80.3 milligrams of whole venom per gram of antitoxin. If all the lethality were attached, for this single toxin. This is the equivalence in toxin that in antivenom that contain this amount of toxin. And the same for this 14.3 at 32.1% of the venom. You have a potency, an equivalent potency in milligrams of venom per gram of antitoxin of 44.7. For the venom yield of the species, which is about 160 milligrams, the amount of toxin that this 167 milligrams contain is 59 of this red and 53 of the green one. This means that to block this amount of toxins, you would need from these antitoxin antibodies 2.1 grams of the red one and 3.7 of the green one. If you do the same calculation, but with the figures of the polyvalent antivenom, which were able to neutralize 4 and 3.6 milligrams of venom per gram of antivenom, and this was venom, then you would need about 41 and 46 grams for neutralizing the full venom yield of this particular species. In terms of antibody toxin ratio in molar terms, this means 2.2 times antibody versus toxin, and this means more antibody to a toxin that is neutralized. So it would be quite interesting to see and compare this data for anti-single toxin with the data in the serum unit, the short chain antibodies or the nanobodies, or even the mini binders that are also now coming into the field. So it would be quite interesting to see how they compare and see if we can improve even these figures. So some more benefits of using purified toxins are an example is here. This is just an example with Naya AG and relatives in the range, and you see everything that has the same color are toxins that are shared between the species in the different populations. So you have a wide range, but fairly good paraspecificity, and some others that are specific for each of the population. So these are the phenotypes that you will find in this range for this Naya species. And If you have pure toxins, you can look for paraspecificity also with the same antibodies that are raised between one toxin if they react against the toxins that are specific for the other populations. And also, if you want to prepare immunogens and you want to have the right amount of different toxins that you may immunize in a single or in different horses to get the best response from the animals. In some cases, you can take venoms that are complementary. For instance, if you want to produce this kind of immunogen and you have these 4 phenotypes, you can mix 47 of B, 30 of D, 28 of C, and you will get a similar composition starting with these 3. But for mimicking this phenotype or this here, there is no possibility. These are like primary phenotypes that you can use for different things, but not themselves to mimic. So would be much better to have the purified toxin, but in this way, if you know the relative toxicity of each of the toxins regarding to the venom, then you can combine in the best way, starting from the purified toxin. So I think that I have, or if not convinced, at least let you think that deconstructing venoms to construct antivenoms approach illustrates the potential for developing broad specific affinity purified toxin targeting antibody sets to construct a new fully Pan-African antivenom with better, if you use them for better immunization purposes. So this is all.